In this lecture, we're going to cover the ZF9HP48. We're going to talk about the theory of operation, and we're going to cover some rebuilding particulars. ZF is a company that makes transmissions, and they'll pretty much sell them to anybody who wants to buy them. So you can see here on this list we have, with the front-wheel drive, the 9-speeds. Honda uses them in their Pilot, Odyssey, Passport, MDX, and TLX. They do use it in a couple other models that are sold in different countries, but these are sold in the US here. And FCA uses it in their Jeep Cherokee, the Jeep Renegade, Jeep Compass, the ProMaster City uses it, the Chrysler 200 before it was discontinued, it used it, the Pacifica uses it, and the Fiat 500X. So they use it in quite a few of their product lines. Matter of fact, ZF makes up like 80% of FCA's transmissions. Not all 9-speeds, not all front-wheel drive, but they are a big supplier to FCA. And then Land Rover also uses it in their Range Rover and their Discover Sport. Those are the front-wheel drive versions of the Land Rover. At the tech, we have Honda units and a couple Jeep ZF 9-speeds. All the pictures you're going to find in these presentations are based off of the Honda units, so they might look a little bit different, but they'll still function the same. The gear set, the way the gear set functions, the way most of the solenoids function, as far as the general operation of this transmission is concerned, everything's going to be the same between them. But just realize that some of the pictures might be a little bit different if you end up going through a Jeep unit. The type of fluid they use is this ZF Lifeguard 9. Honda calls it their ATF 3.1 or 3.1. If you look online, you can find the different pricing, and it's the same fluid. So like this one example I have down here, you can get it as cheap as Mopar fluid. Like I said, these are the same transmissions. You can get it for as cheap as $20. It looks like the same, not site, but the same supplier or same website designer built both of these websites. One of them was Honda parts, one of them was Mopar parts. But you can see the price difference. The retail cost at Jeep is $29, whereas the retail cost at Honda is $48. And then you can get it for as cheap as, well, $20.10 from Mopar. It's the same fluid. Or if you bought it from that Honda parts website, it'd be $33. So my guess is the dealer, if you went to a dealer and bought it, it would probably be, well, the retail, obviously if you had to pay retail, you'd be paying way too much. But if you've got a jobber costs or something like that, you can get them somewhere around that range. If you just pulled the drain plug and drained out whatever you had in it, you get about 3.5 quarts. If you overhauled it, be a little bit more, you'd get about 7 quarts. And even more if you have the all-wheel drive, because the all-wheel drive has the case sticks out a little bit further for the all-wheel drive output shaft and so forth. So it'll hold a little bit more fluid. When you go to check the fluid, Honda has a different method than Chrysler or FCA. And I'm kind of curious, really I don't have any way of doing this, but I'm kind of curious if the FCA method, which uses a special tool to work as a dipstick, would work on the Honda, because Honda has this kind of elaborate method. They want you to, with the scan tool, enter maintenance mode, and then start the engine and shift into the S position. Then on the, that's basically like auto stick. Then on the lift, run it through first, second, third, and fourth gear. Then you shift it into park. Probably want to hit your brakes first, make sure everything stops spinning. Run the engine at idle until it reaches 104 degrees. There's another step in there that I didn't put in there. It says run the engine at 2,000 RPM for a minute to make sure the converter is full. Well, I'd have to believe that if you did this step, that converter sure as well better be full. So then after it's at 104 degrees, and of course you can look at your scan tool to determine that, remove the level plug and make sure the fluid level is level with the bottom of the opening. The level plug is right here on the transmission. So the fluid level should be right across there. And that's their process. It seems like it's kind of a pain in the butt. You'd have to put it on the lift, run it through gears, make sure it's warm. And then obviously if it's not level, you'd have to fill it up to the point where it comes out. Now using the Chrysler method, it's a little bit simpler because they give you this chart with a full range of temperatures. Chrysler's pretty much gone to this with all their transmissions. So if you think you have your shop temperature, actually it looks like 122 degrees is the lowest temperature they want you to check it. So you'd have to wait till at least got to 122 degrees, which is higher than what Honda wanted. And the low, medium, and high range is kind of indicated by these lines. So it could be anywhere from about 17 millimeters up to almost 20 millimeters at 122 degrees. If the vehicle was just operating and it's 195 or something like that, you can see the low level would be as high as 25 and the high level would be about 32. So they don't want to just put a generic dipstick in there because they don't know. They want to trust the customer, or even a technician for that matter, into making sure that the level is right depending on what temperature it is. Where you stick that dipstick tool at is in this spot right here. And now Chrysler will tell you you need to pull that left front wheel, the right front wheel, and pull this plug out, and then you put the dipstick in there. And when you're done, actually it is the left front wheel. You gotta pull the left front wheel, and then put the dipstick in there, and you pull it straight up. They don't want you to like take it out and then turn it sideways because they're worried the fluid will climb up the dipstick. So you pull it straight out, and then you look to see where obviously where the dipstick is crossing the fluid is crossing the dipstick, and you look at the measurement on it and you compare it to your chart to figure out where it needs to be at. There are some TSBs. Honda just has this simple one that basically involves changing this gasket because they get some of these end cover leaks, and that's not really that big of a deal, but there is a TSB on it. ZF has had their issues with the shift quality on these transmissions, and I know Honda struggles with it and Fiat Chrysler struggles with it. Fiat Chrysler and their Jeep products, they seem to struggle a little bit more than what Honda does. As it was explained to me by multiple people, a trainer for Honda and a trainer for Jeep, that ZF sells them these transmissions, and they've got some like base information in these control modules. This is the transmission control module up top, but it's really up to the manufacturer that they're putting this in, like Honda, Jeep, Land Rover, whoever, to have the shift strategy built into the software. So they're supposed to write their own software for these things. They get like I said, supposedly they get like a basic, like it'll run type software built into it, but it's not fine-tuned at all, and they rely on the manufacturer to fine-tune them. Like I said, I haven't read this anywhere, but it's been explained to me. So when Chrysler went through and they first started pushing this transmission into their vehicles, they weren't quite ready for it, and the software was kind of clunky, and it did not. The vehicles did not shift right. Matter of fact, I don't know which gears they left out, but they actually didn't use all 9 speeds on the first release. So you could have bought a Jeep and then maybe only counted 7 gears that it shifted. So as you could probably imagine, there's been a ton of updates as far as software from FCA. But Honda doesn't post the TSBs for their software updates. So the only way you'd find out there's an update for your Honda is you'd have to run this thing in to the dealer, you plug it in, and using their scan tool, it'll tell you if there are updates available. But they're not creating technical service bulletins based on them. Whereas FCA's got a few, they've got a few TSBs. One is kind of interesting. They want you to change this C-clutch snap ring. And when you pop that old snap ring out, they want you to put the new snap ring openings kind of in between this spot here and that spot there. Whereas previously they were located in the middle, where 1 is at. So that was the original snap ring location, then they want you to change that. So here they say install the new snap ring with the openings oriented 90 degrees counterclockwise from the original snap ring location. And that paid, like, depending if it was 2-wheel drive or 4-wheel drive, it paid like 7 hours, 8 hours to take the transmission apart, put it back together and all that. So, and there's a list of things like DTCs and so forth that they attributed to it, or shift quality symptoms. I honestly don't know if this ever really fixed anything. If it didn't break, I don't really see how this could really fix any problems, but maybe the snap rings did break. They didn't really mention that though. They just said change the C-clutch snap ring in the location of the opening. They also had a TSB, this 21-008-19, and it's for reprogram the TCM. And if you look up any model year vehicle that has this transmission, this TSB shows up. And it might not be this exact same number, but it's basically the same thing, reprogram the TCM. And you can see there's a whole slew of DTCs that they're attributing that might be cured by updating this TCM. So you got things like the power control circuit high, unable to disengage drive and reverse, module torque calculation performance, transmission fluid temp sensor A range and performance, stuck in fourth, gear 7 incorrect ratio, clutch position error, unable to engage gear, gear 4 shift incorrect ratio. And then they also have this whole slew of symptoms. So this has shift quality enhancements, but the 2-1 downshift, garage shifts, which means when you're going from park to reverse or drive, poor 3-1 downshifts or 3-2 downshifts, shift. So you can see here there's a lot of, I like this last one, lift foot change mind shift quality. So when you're accelerating and then you lift your foot, does it upshift? Does it stay in the continue geared, the gear you're in? Does it upshift 2 gears? So they're probably tweaking some of the stuff because they're getting some complaints of some weird shifts. And this one was on a 2019. So these bulletins are out there, and they are, like I said, just about every vehicle that if you pick that vehicle and go to TSBs, you'll see one that says reprogram the TCM. This TSB is about adaptation learn procedure, and I'm going to include a copy of this TSB in the folder, the resources folder for this curriculum here. I'm not going to cover, just like the other ones, I'll put all these TSBs up there, but I'm not going to cover each one in depth. I'm just kind of letting you know that there are TSBs, and you definitely want to check these things if you're ever having to diagnose or and work on a 9-speed CF in any of these vehicles, because they've got tons of TSBs, especially with relearns. And even this one, this adaptation learn procedure, in the TSB they talk about how it's different than quick learn, how the adaptation learn procedure is basically involves monitoring these shifts and tweaking them as they go. And it's happening all the time, whereas like quick learn is when you change something and you're trying to reset the adapts and you're trying to get them in a kind of a baseline position. Where here they actually talked about when they first shipped these vehicles, it says here target as shipped, that somebody physically goes through, and they want the same person doing this so that way they get the same feel for what's good and what's bad on what should a 1-2 shift and a 2-3 and a 3-4. And this is what their target is. When they came to the dealer, they're trying to achieve what a subjective evaluation of 6, 7, 8, or 6. If you look, this is the key for that. And so 6 is acceptable, but it's barely acceptable. And then 7's fair, and then 8 is good. So somebody went through and ranked these before the vehicle got shipped. And then after it adapts for a while, these impressions should be better. But the TSB kind of goes through and talks about a few of these little characteristics that you'll find with on your scan data, what it means, and it's actually pretty beneficial to read through that. This TSB covers the warranty extension for this 2014-2015 model year vehicles on these FCAs. And you can see they're probably covered quite a few vehicles. So they're extending the warranty to 100,000 miles. And I'm sure it's because there's been a lot of complaints, a lot of failures, and they are trying to make good on some of those by extending the warranty. Let's get into this ZF 9HP48. By the way, ZF is actually supposed to be pronounced ZF. I guess that's the way the Germans say their Z's, is like a Z. And that's the company. 9, it's 9 speeds. HP, I don't really know what that means, but 48 is the torque capacity. So there's actually a smaller version. I think it's the 9HP 28 or 38, and it's a smaller version that goes behind a 4-cylinder, but all the ones that we have are the ones that go behind 6 cylinders, and really there's no difference in how they operate. The smaller version has a clutch in there that has just like, it's got 2 less clutches, so there's a little bit of difference, but it's nothing that's worth noting. But you can see here it's a 9-speed automatic, not including reverse, so 9 forward speeds. It's got 4 planetary gear sets, and I'd like to point out that the 4 gear sets are located in 3 sections. It's what's fancy is you've got this rear gear set. It has like 2 planetaries, a small one fitting inside a larger one. So you'll see that later on, but it's kind of unique. So I don't really think of this as a 4 gear set, planetary gear set. I think of it as a 3 separate gear set sections. And you'll see when we cover the mechanical power flow of this, it kind of makes sense to look at it in 3 sections. So, and what is pretty impressive, we've got 9 speeds, but we only have 6 elements, meaning 6 clutches or mechanisms to hold or drive things. 2 of them are holding clutches, and they'll be called the C and the D clutch. 2 of them are driving clutches, and they're going to be the B and E clutch. 1 holding dog clutch, and this is something that you won't see anywhere else but on this transmission. And one of them is an F dog, and the other one is an A dog. And they really don't, I guess they really don't need to be called clutches because there's like no friction materials involved or anything like that. But I like calling it that mainly because I can't hardly not call it a clutch, so I just leave that in there. The oil pump, which is pretty common in a lot of these late model transmissions, is off axis, meaning they don't have the torque converter, and then right on the other side of the torque converter where the hub is, they don't have the oil pump. What they have is a small sprocket, and then the sprocket drives a chain, and then the chain drives another sprocket, and then that sprocket drives a pump. So we can save the space that you normally have the pump. You could save that space for other stuff like gear sets. Another thing that these transmissions have that is also becoming popular, especially with like the start-stop technology and all that, is electronic park lock. So when you put this transmission into different gear ranges like drive or reverse or park, in the old days, I mean, most of the vehicles that we drive, I assume, you know, you guys have newer vehicles than I do, more likely, but you have a cable that goes from your column or your floor and goes down and physically moves the linkage in your transmission to put it in park or reverse or whatever. And now they don't have that. Now you basically turn a dial or push a button or something, and you're shifting in between the different ranges, but you're doing so electronically. They still need a mechanism in there to lock a transmission in park, and that's where that electronic parking lock does. There's a little, now this is actually hydraulically controlled from the valve body. A lot of manufacturers will have an electric shift motor that physically has an electric motor that moves you. Here they're using a solenoid to control hydraulics in a valve to move a lever, and that lever locks you in park. There's a park gear in there, and then they have actually a solenoid on the top here. It's called a holding magnet, and it will hold on to the park valve, so it won't ever come out of park until it's de-energized, but or out of the range that it's in. So we'll see some of that stuff coming up, but it's a nice transmission. When you go through this thing, you'll be impressed by how well it's built, and you'll also probably cut yourself a few times because they don't take any precautions or any effort to deburr anything, so it's a very sharp transmission. Be careful. This is the range reference chart, and I've looked in a few different spots where these different information on these different transmissions, and I find different gear ratios, so I'm not 100% certain which one's accurate. Some of these look like rounding, but then again they go to the third digit, but it's like 1/1000ths away. That one's the same, that one's the same, the same. These are all the same here. Then all of a sudden we get to this one, and these are magically flip-flopped. So I don't know if there was a little dyslexia that happened there and somebody just got those numbers backwards, but then these aren't equal either, and those aren't equal. So I don't know, and honestly it doesn't really matter. It probably doesn't make a difference. And there might be a slight difference between the Jeep version and the Honda. I don't think there is, but there might be. Another thing that I noticed is that in some schematics, like this is the Honda schematic that we're looking at right here. Actually it might be, I think that's actually the Chrysler schematic that we're looking at here, but one of them has the D clutch applied in neutral and park, but the other ones don't show it applied. And I can imagine why they would want that clutch applied, because you think of what happens when you're in neutral park. You're going to go to either reverse and it has to be on, or you're going to go to first and it has to be on. So otherwise you're going to have to turn that clutch on when you shift it into one of those two gears. So maybe the way the hydraulics are set up and the solenoid control and the programming, because it's all done through programming, maybe some manufacturers have it ready to go while you're in park and neutral and some don't. So I don't really know for sure what the story is, but anyway, I just thought I'd point that out, that you might find some material that contradicts each other. It probably doesn't make a difference, and I just move on with life. Looking at this transmission, just kind of going around and identifying some stuff. The TCM is mounted to the top of the transmission, and the TCM, it's a ZF transmission, control module. And like I said, the manufacturers are responsible for the final programming in these modules, so that's why they come up with the updates pretty frequently. Another thing that's kind of interesting to note is that this park lever that you have right here, since this park is hydraulically actuated, if for some reason you needed to get a vehicle out of park and things weren't working right in the transmission, they actually sell a special tool, but you can just grab onto it with a pair of pliers and you can pivot this thing away and it'll pull it out of park. I have you guys do that when you rebuild the transmission. You actually pull it out a little bit and we stick like a big nut in there, because if you leave it the way it sits, it's hard to get the valve body out because of the positioning of the valve in there. But you'll see that more coming up later. This is the pinout for the transmission case. And it's kind of nice. We've got a nice little pinout that shows you the name, the colors, and everything that we need to know as far as what's pin assignments and so forth. So we can go through and try to diagnose any kind of electrical issues. Even though the TCM is mounted on top of the transmission, they still have wiring coming from it into this case connector. So it's not like it takes the place of the connector. Some transmissions do that. This one doesn't. And through this we can look at different, solenoids and sensors and inputs, outputs, all that. So if we ever need to evaluate some of the operation of the electrical stuff, we can do it right through this case connector. This, after you pull the valve body off, you see all the solenoids. Remember I was telling you about the linkage that kind of keeps you from pulling the valve body out easily? That's that linkage right there. And it's because the way the lever is and it's spring loaded, it's kind of pushing on the side of the valve body. So when you use that lever and rotate it a little bit, you move this linkage out away from it a little bit there and just put a nut between that and the case, and it kind of holds it out there, and just leave it like that. If you go through one of these in class, in lab, they'll probably still have the nut on there. But that concept in this valve body is the solenoids control hydraulic valves, which control the 6 dog clutches and the hydraulic clutches. The solenoids A, B, C, D, and E, well actually these right here, the orange colored solenoids, we're going to have ones controlling B, C, D, and E, and then a torque converter clutch. And then we have 2 solenoids that are going to control our dog clutches, A and F. And we've got this one actually controls the position of this manual valve. This is a lock mechanism that locks this. Once this manual valve, I call it a manual valve, it's not really that, it's like a park lock valve or something. When that valve moves into the valve body, it grabs onto that little kind of mushroom head that it's got. And then I got a line pressure solenoid. So everything's loaded with, this thing's loaded with solenoids, but they all have their purpose. And we'll see a breakout of what solenoid does what here in a minute. So there are a few different types of solenoids. Some of them are proportional, meaning they're electrically off, hydraulically off. If I don't have any power going to it, no hydraulic pressure is, it's not controlling any hydraulic pressure. Whereas the solenoids that are inversely proportional, if I have it off, it's passing 100% hydraulic pressure. But then as I turn it on, it shuts them off. So there's inverse, they go the opposite direction. This is the layout of all the different solenoids. As I mentioned, the line pressure solenoid, it's inversely proportional, so that way when it's off, it creates high pressure. We want that because we want high pressure. If the solenoid's off, if it ever failed, we'd rather fail it as high. We got torque converter clutch, the E and the B, and the D and the C. These are all proportional solenoids. When they're off, the clutch is off. When they're on, the clutch is on. And then these are also proportional, but they're controlling our dog, F and A. Park cylinder, adjusting the position of this valve right here, and then locking it. So all these solenoids, they kind of have their purpose. Now these solenoids will control a pressure, and that pressure controls a valve, and then that valve controls a clutch. If you notice, there's no accumulators in this transmission of any type. So they're really relying on the accurate control of a solenoid to precisely control a valve, to precisely control the clutch. So the valve body is relatively simple because we've got, out of the 6 clutches, we have 6 valves in there that are going to control pressure to those clutches. And then we have our typical line pressure valves and torque converter clutch valves and lubrication valves and so forth. But it's they rely heavily on computer control and solenoid control. This slide is kind of a work in progress because I'm not 100% certain what a lot of these valves do. Some of them are going to be estimates. Some of them are easy to figure out. For example, if I look at these solenoids right here, I can already tell you with 100% certainty that there's solenoids that are responsible for operating our clutches because it's pretty straightforward. When we look at this, we've got solenoid pressure coming in here. And now these valves, the way they draw this is kind of interesting. This is a picture of a proportional valve. When it's off, the pressure comes in and can't go through. And when they energize it, it's going to let pressure, and it's pulse width modulated, so it'll like a varying amount of pressure it'll let come through and find its way into the circuit. And then when you follow any one of these solenoid driven circuits, they're going directly to a valve that is going to control the clutch. So they're the easy ones to figure out. So all this stuff from here on over, all that is pretty easy to figure out. Those are the solenoids operating their individual valves, which are operating their clutches. Things get a little bit more complicated. Now they do label some of these, so that does make life a little easier. I should say label, they number them. And We've got a couple, like this is the first solenoid is an electromagnetic solenoid, and its job is to hold the parking valve basically in the released position. And number 2 is the park lock solenoid, so its job is to control the park valve. So its output is going to go to this valve, which is likely the park lock valve. Well, actually, that goes to the second layer of the park lock valve, and then that goes to the one. That's where the confusion comes into play. Now, some of these others, like 10, that's our pressure regulator valve or solenoid. And when it controls pressure, it's going to find its way up to the pressure regulator valve. So the pressure regulator solenoid, number 10, is going to end up controlling the pressure regulator itself. This little circle, I'm pretty sure, represents the oil pump, and this little diamond represents the filter. And that's pretty typical. Pressure comes in, and the regulator is going to take any excess pressure, dump it off into the inlet of the pump or the filter, if you want to think of it that way. And then the pressure from our pressure regulator valve is going to end up coming around and working on the end of the pressure regulator, from the pressure regulator solenoid. Pressure from the pressure regulator solenoid is going to come in and work on the end of the pressure regulator valve, and that's going to ultimately raise or lower the pressure as needed. So this valve, I don't know. I put question marks. Maybe it's the boost valve that they call out, and maybe it isn't. I don't know. I have to study this a little further. I do believe this is the solenoid regulator valve. It's a simple valve that basically will cut off pressure once it gets over a certain point, and that's why I think that's what it is, even though it's unlabeled, because if you take a look, it feeds into all the different solenoids. Maybe this is the boost valve. I do not know. But here I'm pretty certain that these are all torque converter clutch related valves, and I believe this is their representation of the torque converter itself. It's got a piston. Notice how all these have pistons. They also have return springs, but in the torque converter they don't use a return spring, so I believe that is their representation of the torque converter right there. And this is the switch valve that switches you between apply mode and released. And then these are going to be, this is going to be your torque converter clutch solenoid. And not only is it going to switch our converter, but it'll also manipulate the pressure that goes to apply the torque converter. And last but not least, we have our oil cooler down here, the fluid that's going to be directed to the oil cooler. So I do realize that this schematic is a little hard to follow, only because the labeling isn't quite clear. I do appreciate the fact that I got something. Most manufacturers don't give you anything. At least this is a start. We'll have to figure it out on our own, but I do like the fact that they at least label out some of these so you get an idea of what's going on. And so there we have it. It's a pretty simple hydraulic schematic. If we knew what everything meant, it'd make a lot of sense. But to look at it, there's not a lot going on. But then again, when you look at the valve body, it's basically solenoid controlling a valve controlling a clutch. And then we've got our pump and our pressure over on one side, and we've got our torque converter clutch stuff going on over here. So there you have it. Some more on the solenoids. You could see the resistance. I'm getting about 5.3 ohms, and that's my proportional ones. These are ones that go to the clutches, B, C, D, and E. And the proportional dog clutch solenoids are higher resistance. They're like 11 ohm. These are all pulse width modulated. The inversely proportional one, which is the line pressure solenoid, it's low resistance. And the electromagnetic park solenoid actually has about 25 ohms resistance, so it's kind of a weird solenoid to operate. It doesn't do anything unless you push the plunger in and have something in there. So it's kind of an interesting solenoid. You'd think there'd be a different way to do it, but it's what they've got. I mentioned earlier that this transmission has 4 planetary gear sets, which it does, but I also mentioned that it's laid out in 3 sections. The front planetary, in these boxes I have drawn out here, don't really fit the picture very well, but this front planetary right there is the output planetary. And the reason why, or even the front gear set, when you think of it that way, because the front planetary gear, this would be the front over on the side, this would be the rear back here. The front planetary carrier has, that's physically connected to this output gear. The output gear is this gear right there. That ends up driving a transfer gear, which drives the final drive, and then eventually the wheels. So the carrier, which is actually this little piece right there, is lugged, there's some like these lugs, to that output gear. And the rear gear set is the one that's got the fancy double carrier setup. This is kind of, without having an actual picture of it, this is a drawing that they had in a ZF book. And you can see they've got a sun gear in the middle, a carrier. See the little plant pinions that we got there? So it's a small carrier. And what makes this thing pretty cool is the internal gear for the small carrier also has teeth on the outside, so it works as a big sun gear for the outer carrier. And so we got this huge outer carrier right here with its pinions, and it's meshing with a really large internal gear. All that stuff is basically right behind this section right there. Matter of fact, this right on the other side of this hub assembly is this internal gear right there. And it is neat because like they will use like this big old blue thing here. They'll use it as a sun gear and they'll hold the internal gear, and then you'll get an output with the carrier, and that's a small gear driving a big gear. Remember, the carrier always acts as the biggest gear, so a sun gear driving the carrier is going to be the best gear reduction. So they can actually use this gear set in the back as a simple planetary gear set just by using the outer, the internal, the carrier, and the sun gear, and just make it work as a simple gear set. Just kind of forget what's going on down here. Who cares about that? And then there's going to be times when they use the inner gear set, and they're going to be like, okay, we're going to drive the internal, and we're going to hold the sun, and we're going to output this carrier. And when they do that, it's kind of a minimum gear reduction because you have a medium-sized gear driving the large gear. And don't worry about this gear set, it's not doing anything at that time. So that's how they get away with this double planetary and that rear gear set, is because there is reverse. They do actually use both, and we'll get in that when we cover power flow, but it's really kind of a fancy setup that they've got there. Another thing that's connected to that rear gear set is that the middle internal gear, which is what we're seeing here. Oh, no, not there. Hold on a second. This middle internal gear is splined, or it's not splined, it's machined into the rear carrier assembly. So I got this rear double carrier, and also connected to that is this middle internal gear. Let me restate that because I might have said it wrong. We have this rear double carrier assembly with the 2 sun gears, 2 internal gears, 2 carriers, and also part of that is the middle internal gear assembly. So in the middle gear set, I have that internal gear and rear carrier as kind of together. Hold on a second, I should have underlined those. Right here. The rear carrier is connected to the middle internal, and then when we get to the middle gear set, the middle carrier is connected to the front internal. So we've got a rear carrier that's hooked up to the middle internal, then we have a middle carrier that's hooked up to the front internal. So they're kind of doing the same thing from front to back. When we look at power flow, you're going to see this transmission is pretty cool because they have the rear gear set feed the front, or the rear gear set feed the middle, and the middle feed the front. So depending on what they're doing in these 3 gear sets will tell you what gear you're in. For example, in first gear, they have the rear gear set with those double carriers working a max underdrive. Then this will work in a minimum underdrive, because that's the only thing it can do. Minimum underdrive. And then the front gear set works in a minimum underdrive. That's first gear. Rear times middle times front. That would give me my first gear ratio. When I shift in the second, they switch this rear gear set. They take it out of maximum underdrive and switch it to minimum underdrive. Now it's minimum times minimum times minimum. When you shift in the third, they're going to direct drive this rear gear set. So direct drive times minimum. That's third. When they shift in the fourth, they're going to direct drive the middle gear set. Direct drive, minimum. And you can probably guess when they shift in the fifth, they're going to direct drive all three. And we'll keep going with powerflow, go through all the other stuff, but surprisingly, in order to get the overdrive units, they end up going back to underdrives in the rear gear set, and that causes parts in the middle and the front to spin faster than input shaft speed, which end up giving us the overdrive. We'll see that stuff when it comes up to the powerflow section. Some of these common connections or job descriptions, if we were to look at it, we have this E-clutch. You can see on this whole gear set, this E-clutch is really kind of falling in this area right here. Up in the upper left corner, I'm kind of throwing the full gear set, kind of letting you know where this E-clutch stuff is located. You can see when it's applied. It's applied 4th through 9th gears. And the purpose of it, this E-clutch right here, is going to take input shaft speed, because that's what this drum is hooked up to. And when that clutch applies, it's going to deliver it through the shaft, and it's going to driving my middle carrier, say MC, and my front internal. When I take this thing apart and check it, I should have between 30 to 70 thousandths of an inch of clutch pack clearance while I'm placing 45 pounds of force on the clutch. So these clutches, all the clutches in this transmission, when we check it, they want you to put 45 pounds of force on it when you check it. Here's our B clutch. You can see it's kind of blown up there. One of the things that's unique about that's in the very back of the transmission. And they've got two single-sided frictions, and they live on either ends. So like there's one here before this big thick plate, and then there's one on the complete other side. So it goes single-sided, then double-sided steel, double-sided steel, double-sided steel, double-sided, single-sided, and then plate. And this piston here, if you take a look, see all these holes? See all these holes. This thing does not do a very good job when you air check it. And they kind of have balance oil going on and all this other stuff. Like this is a apply piston right up here, and it fits inside this housing. And then this is like a balance piston that lives in there. And balance pistons, they're designed to bleed oil off into the balance piston area, and it kind of leaks out naturally through the inner surface there. And it just, but it makes for a horrible air check. A lot of these, you have to air check with 60 psi to get it to apply and sound right. So what its purpose is when I apply this, is I'm going to drive, because it's, even though I have the circle back here in the upper left, and it looks like I'm pointing at the shell, it's actually the clutch that's inside the shell. So that's where the E clutch is at. This is actually the C clutch that rides right on that surface where those lugs are. The B clutch is going to be on the inside of that surface there. So, and it is a driving clutch. So the one of the other things that you'll find is that there's the smaller version of this transmission has a tighter clutch pack clearance. It's because they don't have those single-sided frictions in there. They leave those out apparently on those. But when does it apply? We look at it, 3rd, 5th, and 9th. In reverse. Yep. This is the F dog. And I got a video showing this thing engaging and not on the next slide. But it lives right inside this area right here. You can kind of see, looking at this picture on the upper left, we can see the output gear right there. And then what you don't see is that there's a sun gear kind of in the middle in all those gear sets. This is the output gear on this picture right there. And you can see it in all these pictures. But these teeth that we have on this sun gear assembly, those are the dog teeth. And then there's a matching set inside the output housing here. And if you take a look at these pictures, you can see this one shows the dog is down, and this one shows that the dog teeth are up on the little apply piston in there. How does it shift? Well, it does so through hydraulic pressure. You can see I'm pumping air into this passageway and it pushes it down. And then when I pump air into this passageway, it lifts it up. So when this is in the up position, it grabs onto these dog teeth. And then it locks that sun gear, which is a combined sun gear between the front. Maybe the front would be using that half of the sun gear, and the middle would be carrier would be using the other half of that sun gear. So when this is shifted up, like we see it in this lower left, it's going to lock those dog teeth and the sun gear. It's going to lock it to the case. Don't be tricked because you see the output gear here and you think this is spinning with the output shaft. There's a big bearing in there, and this is just a support assembly. So this part in the middle here is basically fixed to the case. It's bolted down to it, so it won't spin. So when I apply that dog in the up position, this sun gear is now held stationary. And then when this dog gets pushed down, the dog is free, and it will spin on its own. It is not connected to the case anymore. That's why they have this Torrington bearing in there, to let that spin freely when you are in fifth gear and higher. The A-dog clutch works in a similar fashion, but instead of being a holding dog, this is a driving dog. So over here, it's looking at the upper left again. This is where the A-dog would be in the center of this whole assembly that you see there. And here is looking at the pictures on the left side. These two show the two positions of the A-dog. It's either going to be forward or rearward. And realize that this whole assembly is like pinned through that little pin assembly. It's pinned through a slot to the main the input shaft. So if the input shaft is spinning, this dog assembly is spinning. And what it grabs onto is that rear gear set uses that sun gear / internal gear that I kind of mentioned. Remember, we've got a double gear set. There's a good picture of it here on this side. We've got an inner planetary, or the big outer planetary. We have an inner sun gear / internal, and then behind it, you can't see it, but there's a planetary gears in here, and then in the very middle, there's a sun gear. So this is that dual planet setup in the rear gear set. We have a sun, pinions, internal gear. Built into the internal gear, you have a sun gear, then planets, and then an internal gear that would mesh with these big old planets. So what the A-dog does is it drives this gear that lives in the middle there that works as either a sun gear to the big planetary gear set, or it works as an internal gear to the small planetary gear set in the rear gear set. That's what these in the middle here, you can see where the lugs on the A clutch or the A-dog grabs onto the lugs that we see on that combined internal / sun gear assembly. So when is it applied? It's applied for a good part of the time. in 1st through 7th gear. So only 8th and 9th gear is this released. And so this is a major input in this transmission then. The A dog, it's going to be driving this large sun / small internal gear assembly. And the video on the next screen will kind of show you how it can do that. Next, we get to see how the C clutch, how it does its job. It holds that rear sun gear. If you remember, we talked a little bit about that, or I just briefly mentioned it. When I was talking about the B clutch, the picture looks about the same, but the B clutch lives inside the drum over there, whereas the C clutch grabs around to the outside, those lugs. It's a holding clutch, so if you stop and think about holding clutches, their job is to hold a gear set to the case. So that's why we oftentimes see the splines that are real large on the outside of a gear set. Those are the holding clutches because they're going to be between the case and those hubs. And what its purpose is to hold the rear sun gear, that small rear sun gear in the back. When the C clutch applies, it holds it to the case. And it will do that in 2nd, 6th, and 8th gear. When you check this, this is one of those clutches that might change. Actually, take that back. I don't think this one changes at all. But you're supposed to put 45 psi, and I'll be curious to see what you guys get. But I get the same reading, or within a few thousandths, whether I have 0, 45, or 100 pounds of force on it. Doesn't seem to make a difference. But it's a little tighter clearance, 30 to 45 thousandths. There's just not as many clutches, so usually the lesser amount of clutches you have, the tighter the clearance. There's supposed to be roughly 10 thousandths around each clutch. So if you only have 3 clutches, you're probably only going to have 30 thousandths or so of clearance. And then the D clutch sits right next to it. It's actually the first holding clutch that you see when you take the transmission apart. And the D clutch's job is to hold the rear internal gear, the big internal gear. Remember that rear gear set has 2 planetaries, the sun gear / internal gear in the middle, a small sun gear, and then a large internal gear. And the D clutch's job is to grab onto and hold that large internal gear from spinning. It's applied in 1st, and then 7th, 8th, and 9th. Reverse, and then the Fiat Chrysler also shows it listed in park and neutral, but Honda doesn't indicate that. I think they probably do have it applied because, like I said, if you have that D clutch applied in park and neutral, the 2 places you're likely going to go are reverse, which you need it, and 1st, which you need it. So you might as well have it applied when you're in park and neutral. It also says the clearance should be between 40 and 59 thousandths with 45 pounds of force on it. This picture right here looks really wild. It's took me a while to draw this guy, you can probably imagine. But I basically, to break down how the power flow worked, and you've seen this in other transmissions that we talked about, is I made just my own little connection so that way I could figure out what's doing what. And so we'll see in a second here, I kind of build this up and what the common connections are, but this gear set that we have is being represented by that block diagram, which I'll explain now. First, we kind of look at what the case is and what the input parts are. I got the case drawn black because, I don't know, I just use black. But so anything that's in black is going to be held to the transmission case. You can also see I've got, this is the output gear. And the output gear has a little bearing That's what I've labeled it, the output gear bearing, and then the output gear itself. So when we see the output gear and the output gear bearing, that's what this is, how it's represented on this drawing. And the input shaft coming from the torque converter, it has the ability of driving the E-clutch assembly, and when that clutch is applied, it'll go through the hub and so forth. Then it also has the ability of coming in and driving my B-clutch, and it also has the ability of driving the A-dog, because that's splined to it. So those are things that are always connected to the input shaft. Now what did I add here? Still got my input shaft, still got my case and my output gear. I added the forward carrier, the front carrier, because the front carrier is always lugged. It's got these little, it's actually kind of the opposite of this. The carrier has the openings, and the output gear kind of pokes into the openings, kind of lugs itself in there, but it really doesn't matter. Just they're lugged, they're connected together. If my front carrier is spinning, my output gear is spinning, and I'm moving down the road. Now I added the next level. So you can still see the only thing I have in the front gear set is my front carrier, but now I added the front internal gear. And the front internal gear is connected to the middle carrier. That's the middle planetary pinions. And disclaimer, these things aren't to scale or anything like that. I sketched it out on a piece of paper, then I drew it based off of my sketch. Even when I was done, I kind of looked at it and said, man, these things aren't quite to scale, but it doesn't matter for the sake of just trying to understand what gears are what connected to what. Once again, I tried to stay with the consistent color. So our B clutch, when it is applied, it's going to drive the shell that can come in here and drive my middle carrier and my front internal gear, because those are all common. Now I added another layer here where I've got that double planetary gear set in the back, and that's my outer pinion or pinion gears on the larger. Those would be equivalent to these gears right there, and then the smaller planetary pinions, those would be the ones that live inside there. So this is that double planetary gear set that's in the rear gear set, where I've got the small planetary gear set, the small sun gear. Well, these are representing the small planetaries, and the large planetaries are the ones on the outside here is drawn. So small, large, or outside, I guess say inside, outside, or something like that. So these would be the inner planetary pinion gears. And then these would be the outer planetary pinion gears. And they are all connected. They're all connected as one. And you can see what also is connected to that rear planetary gear set. It's the middle internal gear. These planetaries are always going from planet to an internal gear, planet to an internal gear. So they're consistent in that fashion. Now I added in the rear gear set, I went ahead and added that sun gear slash internal gear assembly. So this is going to work as a small internal gear on the inside, and it's going to work as a really large sun gear on the outside. Same part, sun gear on the outside, internal gear on the inside, and then we know what this is. This is where that A-dog grabs onto, and the A-dog is represented by this little box down there. So it looks like the way I have it drawn now is the A-dog is going to drive and connect to this middle sun gear, large sun gear slash small internal gear assembly, and that lives there. So this section here is working as an internal gear to the small planetary, and then this part right here will act as a sun gear to the large planetary. Hopefully that makes sense. So you can see we're slowly starting to build this thing up to the point where we'll have a complete gear set and drawing. Now what I added here is the internal gear to the rear gear set. So this is just the internal gear to the rear gear set. So now we actually kind of have one complete gear set. The large outer gear set has a sun gear right here, a carrier, and an internal. And what can we do with that internal gear? Well, the D clutch is going to be able to grab onto that. So this right here is where the D clutch grabs onto, and it locks this internal gear to the case. Now I add my C clutch and my B clutch. So I've added this small sun gear to the mix. So now this rear gear set's pretty much complete. I've got a small sun, a small planetary pinions, the small internal gear that's also going to work as a large sun gear. Then I get my large planets and my large internal gear. And what can I do with that large internal gear? The D clutch can hold it to the case, and that's about it. Now what can I do with the sun gear? As you can see, I can hold it to the case through the C clutch, or if the C clutch is released, I can go through the B clutch and I can drive it at input shaft speed. So that small rear sun gear can be driven or held. Now I added my F-dog and my gear set is complete. My F-dog is this front sun gear, or drives this front sun gear, connects this front sun gear, doesn't drive anything. The F-dog connects this front sun gear, which is common between the front two gear sets. You can see it spans, that's why it's so tall. This gear set's so tall because there's actually the front gear set towards the front of the transmission, and then the middle gear set is behind it. So it's actually a common sun gear between the front and the middle gear set. Using my F clutch, I can lock it to the case. You can see when it slides and engages both, it's going to hold the sun gear to the case. Remember, everything in black is the case. And then if I move the F-dog, retract it, basically get it out of the way, then my sun gear that's common between the front and the middle gear sets, it's actually not going to have any connection at all to the case. It'll be able to just basically operate between those two gears. And they do that primarily in the overdrive. Direct drive and overdrive, you'll see, is when that F-dog releases. So 5th gear and above. Now at this point here, hopefully you've understood this drawing well enough, and we can actually go through and see what happens through these gears. This is going to be first gear, and when we look at first, we see our A clutch is applied, that's the A dog, and our F dog is applied. So both of those are applied, and then our only other clutch that, other than our dog clutches, would be the D clutch. But remember that with the A clutch applied, torque is going to come in, it's going to go through that A dog assembly, and now it's going to drive this middle gear set here, and that's that that small internal gear / large sun gear. Well, we're going to use it as a large sun gear right now, because if you look at what I'm holding, my D clutch is holding this internal gear to the case. So my internal gear is going to be the input. That's I for, no, I said that wrong. The internal gear is going to be held. That's H for being held. My sun gear is going to be input because the A dog is going to deliver torque from the input shaft through the A dog into this sun gear assembly. So my output to this rear gear set is going to be this large carrier assembly. And it's going to be at a strong gear reduction because I have my smallest gear, the sun gear, is input, and my largest gear, the carrier, is output. And also connected to that assembly is the middle internal gear. So this rear gear set basically outputs in a gear reduction to my middle gear set. What's being input to my middle gear set? the internal gear. And it receives that input from the rear gear set. What's held? The sun gear. So then my carrier is output. You can see that's a minimum underdrive, where I've got a medium-sized gear driving a large gear. So I got maximum in the back, and I got minimum underdrive in the middle. So what does that middle gear set do? Well, it outputs to the front internal. So now to the front gear set, the front internal is the input. The front sun is still held. It's a common sun. And then my output is my carrier assembly on the front gear set, and ends up connecting to the output gear. So what I have is I have a maximum underdrive driving a minimum underdrive, and a minimum underdrive driving minimum underdrive, and then overall that ends up giving me my first gear ratio of a whopping 4.7 to 1, which is a really low ratio. So maximum, minimum, minimum, by the time you multiply all three of those together, you get a pretty good first gear ratio, if that's what you like. I think that's a lot lower than practical, but that's my opinion. Now we shifted this transmission to second gear. And if you take a look, they don't have the D clutch applied anymore. What they did is they released the D and applied the C. All they did is this single clutch release and single clutch apply. That way they can synchronize the shifts and make it nice and smooth, and hopefully not have any issues. What I've done now is I've taken what was being held was my large internal gear. That's not the case anymore. Now I'm holding my small sun gear. I still have my A-dog applied, so I'm still delivering torque through the A-dog into this middle sun gear assembly, or this middle gear assembly. But now instead of going up to the large gear set, I'm going to use it as input on the internal gear. We're going to use the smaller of the two gear sets in that rear gear set. So I have a sun gear that's held, I have a small internal gear that's input, and my output is this small carrier. And that's going to give me a minimum reduction because I've got a medium-sized gear, the internal gear, driving a large gear. And that's going to output to my middle gear set, which is still operating the same as it was in first. And that middle gear set's going to operate to my front gear set, which is still operating the same as it was in first. So where the gear ratio change occurred is by going from a maximum underdrive in this rear gear set to a minimum underdrive. I was able to take some of that gear reduction away, and now we've got a little higher gear between first and second. You see the ratio dropped to 2.824 because I have a minimum underdrive feeding a minimum and a minimum underdrive feeding a minimum, and by the time you multiply all three of those together, that's what the ratio you end up with is 2.824. Now when we shift this transmission to third gear, you can imagine what maybe you're getting a grasp on the concept here. We're just going to direct drive that rear gear set. So if we apply the B clutch, the B clutch is going to come in and drive this rear sun. And if we still have our A-dog applied, which we leave it applied quite a bit, so it's still applied, we're going to end up driving this sun/internal. So think of the small gear set. I have the internal gear as input through the A clutch or A-dog. I have the sun gear as input through the A-dog. That makes the small carrier spin at input shaft speed. I really should color this red. And now that this is going input shaft speed, the middle gear set and the front gear set are still doing the exact same thing. I've got, the only thing that really changed is my internal gear is now spinning faster because it's directly driven, as opposed to having a maximum underdrive like it did in first or a minimum underdrive like it did in second. So now my input to the middle gear set is going faster. That causes my input to the front gear set to go faster, and my overall gear reduction in third gear is 1.909, which is a pretty good step from second gear. And I got direct drive driving a minimum underdrive, and a minimum driving a minimum, and that's my third gear ratio when I multiply all those together. So hopefully you're getting the concept. You can probably imagine what's going to happen next is if now they're at the point where they directly drove the rear gear set, maybe they're going to change this gear ratio. We'll see. And you're right. That's what they did. They applied the E clutch here all the way up in the front. And what that does is the input shaft goes through the clutches, to the hubs, ends up driving this hub assembly, which goes in and drives the middle carrier slash front internal gear at input shaft speed. So these are all inputs. And then I'm still holding my front sun gear. So really the rear gear set doesn't have to do anything because I'm directly driving at input shaft speed my internal gear in the front gear set, and I'm holding my sun gear in the front gear set. That makes my output at whatever gear reduction I can get out of that front gear set. So it actually shows the pure gear reduction that we have in that front gear set when this transmission's in fourth gear. So that front gear set only produces as a complete gear set with something held, something driven. This is the minimum gear reduction it gets. It's not like we're taking a sun gear and driving the carrier. We're taking the internal gear and driving the carrier, but that's at a 1.382. Now you can probably imagine what's going to happen next. If they, in third gear, they had a direct drive in the rear gear set. In fourth gear, they direct drive the middle. And they didn't even have to do that because it's connected to the front internal. You can probably imagine when they're in fifth, they're going to direct drive the whole gear set. And so we got a lot of red going on here. Fifth gear, we have the A clutch is applied, the B clutch is applied, so those are our driving clutches, and the E clutch is applied, another driving clutch. There's no holding clutches applied when we are in direct drive. They can't, or else this thing would lock up. So they have to, if they kept that A clutch applied, then we know we're driving this middle sun slash internal gear assembly. They have the B clutch applied, which means they're going to end up driving this rear sun gear assembly. So we know this rear gear set's going direct drive, and it's feeding this middle gear set. If this middle gear set's going input shaft speed, the carrier, because the E clutch is driving it, and we know my internal gear is going input shaft speed because of the B clutch and the A clutch in the back. There's a lot of lines on this, I know. That means we have these two gear sets going input shaft speed. And since the middle gear set is connected to the front internal, that's going input shaft speed. And since the sun gear is now going input shaft speed, my front carrier has to go input shaft speed. So it's just one big old block of red. Everything's going in direct drive. This is where things get going pretty tricky. Just like in direct drive, my F clutch was released. So my sun gear, my front sun gear does not get held to the transmission case anymore. It has the ability of operating these two gears, the front and the middle gear set. So I wrote down what the overall concept is here. And this is really slick the way they do it, and I wouldn't be surprised at some of the noise complaints, which I don't know if you can actually hear when you get up to like 8th or 9th, but this front sun gear is really singing and when you're in 9th gear. The overall concept is that by spinning the rear gear set in an underdrive, the front sun will be forced, this guy, it's in blue, light blue, is going to be forced to spin faster than the input shaft. And if I'm spinning something faster than the input shaft, and everything else is either going input shafts, like the front internal gear is going input shaft speed, if I spin the sun gear faster than the input shaft, well then you know the carrier, the front carrier, is going to have to spin faster than the input shaft. So what they're doing, the concept is as they change the gear ratio of this rear gear set, they'll go from a like a minimum reduction to a maximum reduction to holding it, and then they'll actually make that rear gear set, the rear planetary, spin backwards. That forces this front sun gear to spin faster and faster and faster and faster as you go through 6th, 7th, 8th, and 9th gear. So take a look at what's happening here in 6th. We are still driving our A-dog is still engaged into that middle sun slash internal gear assembly. But what's it doing? We have our sun gears input, our small sun, because of the C clutch, is held, which means our rear carrier is output, the small rear carrier is output. That ends up feeding in a gear reduction. It's a minimum reduction, not a maximum reduction, because I have an internal gear driving a carrier. So it's spinning in a gear reduction, but not the best in the world. It's spinning that middle internal gear, so it's slower than input shaft speed. Well, we still have my E-clutch applied. Input shaft is driving the E-clutch. E-clutch is driving the middle carrier and front internal gear. So if the middle internal gear is spinning slower than input shaft speed, the carrier is spinning faster, or spinning at input shaft speed, it's going to actually cause the sun gear to spin faster than input shaft speed. So I'm going to put F. This is spin faster. It's common sun gear between the middle and the front, so now my front sun gear is spinning faster. This is going input shaft speed still because it's all connected. The front internal middle carrier is all being driven input shaft speed by the E-clutch. That causes the sun gear to spin faster, which delivers a faster rotation to my front carrier, and voila, I get my first overdrive, which is a 0.808 to 1. And when you play with these gear sets by hand and you force this to happen, you can see that sun gear spinning faster than the input shaft. Now we shift this transmission in the 7th gear. That concept here, kind of going off of what we were talking about before, is we are still working this rear gear set in an underdrive, but what we want to happen is we want this rear gear set to, it was going at a minimum underdrive in 6th gear. We want to go at a maximum underdrive now. We want to go a lot slower than input shaft speed. So, because the slower we make this carrier spin, the slower we make this middle internal gear spin. The slower we make the middle internal spin, the faster we'll make this sun gear spin. And if as I make this sun gear faster, it's going to make my front carrier spin in a greater overdrive. So so this is what we're doing now. We still have our A-clutch applied, and it's still driving the sun slash internal assembly, but now we're not doing the small gear set, we're doing the large gear set. So this is working as a sun gear, and this is input, SI. The carrier is output, internal gear is held. So that's going to work at the best gear reduction we get. And input is a sun gear, output is a carrier. So this is going to be spinning much slower than it was in 6th gear. It's still going to be working at a gear reduction though. It's not going to be stopped. So if the middle internal gear is spinning slower than input shaft speed, even slower than it was in 6th, as this middle planetary gear set, which is driven by the E-clutch, is still continuing to spin input shaft speed around or within a slower moving internal gear, that forces this middle sun gear to spin faster, even faster than it was in 6th. That's a common gear between the middle gear set and the front gear set. The front gear set still has the input speed coming from the E-clutch to the internal gear, a faster moving sun gear, and now even a faster moving carrier driving this in a nice stronger overdrive at 0.699 to 1, about 7 to 1. That's where most overdrive transmissions, that's where most of their overdrives end. They don't usually go much higher than that, but this transmission does. Now we shift it into 8th gear. So we've been moving this carrier. In 6th, we slowed the carrier down. In 7th, we slowed it down even more. And now you take a look what it did in 8th, it stopped it. Now the carrier, this rear gear set basically is stopped. It cannot move. That A-dog is released. It is not connected to the input shaft anymore. So I can stop, I can hold stationary by applying my D and my C clutches at the same time, by holding my sun gear, my small sun gear, and by holding my large internal gear. I basically lock this whole gear set up. It's not moving. So that means this middle internal gear is stationary. So it's not moving at all. My input gear is my input to this middle gear set is still through my E clutch. It's still my middle carrier. And now we've just caused this sun gear to spin even faster. We have the largest gear in this transmission driving the smallest gear, which is the greatest overdrive you can get if you're just holding something and driving something. So this middle/front sun gear assembly is spinning very fast for the front gear set and for the rear gear set. So in the front gear set, the front internal is still going input shaft speed, but now my front sun gear is singing away, spinning very fast in an overdrive fed to it from this middle gear set. And now my front carrier is spinning very fast, very, very fast. So 6th gear is spinning fast. 7th, very, very fast. 8th gear, very, very fast. Wait, very, very, very fast. So you're like, wait a minute, now you've just held the rear gear set. How are you going to do any better than that? How could you possibly make that spin any slower if it's already stopped? Well, those guys at ZF, guys and gals probably at ZF, said, well, why don't we stop this from spinning, but maybe we can make it spin backwards. And that's what they do for 9th gear. So 9th gear, they hold that D clutch that holds that internal gear that's being held with the B clutch applied. So they release the C and apply the B clutch. Now I'm inputting my small sun gear, and the reaction that occurs by the small sun gear rotating clockwise, and then this pinion rotating counterclockwise, and then this internal gear rotating counterclockwise, which is working as a sun gear, which is counterclockwise on this gear set, which is going to cause this to rotate clockwise. You end up getting this reaction that occurs between this whole gear set, and you end up getting a gear reversal. I don't know if my arrows worked, but I'm going to erase them so that way you can't really prove anything. But what ends up happening, and I can show this pretty easily on the gear set, when you do how this thing is laid out, and you drive this rear sun gear, hold the large internal gear, this gear set actually rotates slowly in a counterclockwise direction while everything else is rotating in a clockwise direction. That really makes this sun gear just sing away, go fast. So it's going super duper fast. So it's going very, 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 very fast. Or much, much, much faster than the input shaft speed. And that causes my 9th gear overdrive. And there you have it. So all these gears and with just 6 clutches, hopefully you followed along with that. I know there's a lot there, but the concept is not that complicated once you understand it. If you understand it, it's not too bad. If you are lost on it, then it's probably like I'm speaking a different language. Well, we can't forget about reverse. If we take a look to see what's applied in reverse, we have the B clutch, the D clutch, and our F clutch. Our F clutch is going to hold this front sun gear just like it did, 1st through 4th. And our B clutch is going to drive this rear sun gear, the small sun. And just like in ninth gear, where we get reverse rotation out of this carrier assembly by holding our D clutch and driving our B clutch, or having the input be the small sun and having the large internals being held, that reaction causes this whole carrier to spin in a reverse rotation. Now if I go ahead and hold my sun gear assembly, I can get more gear reductions. My front sun. If I hold this, use the F dog to hold this combined front middle sun gear assembly, you're going to see that now my reverse input, I'm going to do an RI because it's a reverse input now, coming in from my internal gear. With the held middle sun gear, my output is going to be in reverse the carrier, middle carrier, and that's going to feed a reverse input to my front internal gear. Still have my sun gear held, it's common, and that gives me my output. So I get reverse reduction feeding a minimum reduction, feeding a minimum reduction, and that's what I get for reverse. And it's a pretty low gear for reverse, 3.805. Now this might make a little more sense when you look at these drawings. This connection here just basically shows you what you're looking at. I know there's a lot of arrows and boxes and all that stuff, but just take a look at it for a second. The D clutch is going to be connecting on that drawing. It's going to be connecting there. It's also going to be connecting to that part. The F clutch is in the transmission, in the gear set. You can't see it, but if you had X-ray vision, it'd be in there somewhere. The E clutch is this one in the front. It's the driving clutch that's in the very front, and we could see that. By the way, these are sharp. You put your fingers in there, you'll cut them just by squeezing them. I got cuts in my fingers to prove it. The C clutch is this rear holding clutch assembly, and that's represented by that on the diagram. And then the B clutch is inside that C clutch drum, so you can't really see it, so that's why I have the arrow just kind of pointing to the end. But that's basically showing you what you're looking at here. I know I got arrows. I added arrows on top of arrows, which is probably maybe more confusing, but when you're looking at this drawing, it might make a little bit of sense once you've made these connections between the drawing that I made right here versus the actual gear set. Hopefully you understand it at this point. When you take this transmission apart, you'll notice that some of these valve body bolts have like thicker shoulders. A lot of them are tapered like that. You can see the little tapers that they got on these. And then some of them have these like, they stick out like 1/8 of an inch. Those are the ones that you need to take off to get the valve body off of the case. You don't have to take all the little Torx head, you have to take the Torx. You don't have to take the tapered headed ones out, just the ones that stick away from the valve body. And also, I don't have it up here, but take a pair of pliers, twist this, and then grab like a pretty good sized nut and put it in there. And that will move this lever over far enough to the point where this will slide out, because right now it's applying force in that direction, and it's going to make that valve body hard to pluck out of there. Pry gently when you get that. When you try to get this valve body off, you're going to fight these O-rings a little bit. They'll either leave the tubes, like these were left in the case, or they'll either be left in the case or they're going to be left in the valve body. But the O-rings are going to have a little bit of resistance to it. So it's best to pry it in a few different spots. I kind of like this little cutout right there that they've got. You can get something in there. Just be careful. Don't pry from a spot where there's bores, like the ends of the valve body where there's valve body bores. Don't pry in any areas where you can, like there's some thin spots on the valve body. You wouldn't want to pry on that either. You don't want to crack or break anything. So just wiggle it, start prying on it, wiggling it a little bit. It's not going to need much force. If you need any real force, you should see the valve body moving. If you need any real force, there's probably a bolt that you missed that's still holding it in there. And we don't want to make a big problem out of a small problem, right? One thing I also mentioned before I skipped this, and I think it shows up in others, when you take it apart, notice that wiring harness here. See how it kind of goes around? It's very easy for this thing to flop over and get in the way of the actual case casting right there. And if that happens, you'll pinch that wire there and you won't get it, you'll probably screw some stuff up. So there's even a little spot, this little thing right there, where you can kind of tuck this wiring behind it when you go back together with it. As you're doing some measurements, it's kind of nice. They give you these little windows. I don't know if that's really why they're there, but like when you do a clutch pack clearance check and you got that force gauge in there, you can stick your feeler gauges in from the side and measure it. When you go to pull the harness assembly out, like right now everything's still assembled, we have to take a little Torx bolt out that's right there. That's a range sensor that we have. You take that bolt out right there, and this is a dual speed sensor assembly. And then there's a clip on the top. You pull this off. It's really, all this stuff is really easy to do. And then you can push the connector through, and now you got your valve body off to the side. This is really nice, is the ability to go through an air check, all the different clutches easily. So between the valve body and the case, when they're applying these clutches, this is how the fluid gets into the holding clutches, into the shafts and all that stuff. Now these teardrop shaped holes are kind of a pain. You can't really just stick a nozzle in there. So I've got like a Sonex wet air plate that I've drilled holes in so you can bolt it down. But even so, you can't put a lot of pressure on it or else it'll kind of flex the plate or the gasket and it'll just kind of make a squeaking sound. And they don't air test. Most of these don't air test very well. So when you pump air into it, you will hear air leakage. But with a 30, 40, well really 40 psi, most of these clutches, you should be able to hear it, like thunk, thunk, even if you hear a lot of air leakage. And some of them, like through these windows, you can actually see the pistons actually moving and compressing the clutch pack. So, believe it or not, through the speed sensor hole, you can actually see, if you rotate the input shaft a little bit, you can actually see the E-clutch even apply through there, because it measures through those razor sharp windows that are cut into the E-clutch housing. When you see the term on, that means like it's locking the sun gear to the input shaft, and the F dog is going to be locking the sun to the case. So if you pumped air into this passage right here, that would actually move that dog assembly into the locking mode. And when you pump air into this teardrop passage, it's going to be moving that A dog into the apply mode, where it's going to be driving that middle sun / internal gear. Bell housing, once it's removed, which it is easy to do, you just take the bolts off, the Torx bolts that go around the case. It's very easy to assemble this transmission, and some of these parts are heavy, but it's not really nothing's difficult as far as that's concerned. There are some special tools. I was able to make every special tool using other transmission parts. The tools, some of them are really, even from the dealer, they're too cheap to almost make on your own. The only time I think you'd make it is if you needed to build this thing and you didn't want to wait however long it takes to get these tools shipped to you, or if they're back ordered or something like that. But if you had to make them, they're not that hard to make, and you can go that way if you needed to. When you remove the differential and the transfer gear and the E-clutch and all this stuff, you can start pulling these things apart. One of the things you'll notice, the first thing, is that these lugs right here on the output gear, they fit into these openings on the carrier. So that's how that front carrier has the ability of driving this front output gear. It also keeps these things in really close quarters to each other, and that saves space in the transmission. You can tell the engineers are tasked to keep it as compact as possible, so they have very little or really no wasted space in these transmissions. Another thing that's worth mentioning in here is this, and we saw it with some of the previous slides. The sun gear's in this front gear set, and this section right here is what the dog teeth will grab onto, and you can actually see the dog teeth in there a little bit, and they'll move up and down to grab and release, which we saw a video of that. Once you get those parts I previously mentioned out of the way, before you take this D-clutch housing out, you're gonna have to pull this bearing off. I guess to save space, they overlap some of these things. I don't know, but here's the big thing. There are reliefs cut in the case for the ends of this bearing right here, these pullers, and you'll see it when you take it out. But the key is don't just put the 2-jaw puller on there and start pulling that out, because if you grab only the cage, you'll distort that bearing and ruin it, and we don't want to do that. So moving around, you'll find the little spots where there's kind of some machined section out of the aluminum underneath it, will allow you to get these pullers underneath the inner race of that bearing, so that way you'll be able to pull it off safely. There's also like an oil dam or something on the aluminum there, so you can't just put the end of the puller on it. There's something in the way, so you have to kind of put a socket. I don't remember, it's like 24 millimeter or something like that socket that just kind of lifts, gives you something. It goes over that little gutter thing that's sticking in on the aluminum case, and it gives you something to center your puller on. And when you take it off, you're going to find that you got a shim under there, and it's just something you don't want to leave out when you go back together with it. This is the Miller tool that they want you to buy. This is actually an expensive tool. It's like the whole kit comes these little long fingers, these long fingers that go all the way down, and the compress on these parts, and this little cross assembly is like, well, it's $350. You can buy on eBay the tool, because people steal these rings from the dealerships and sell them on eBay for 113 bucks, and they don't come with the fingers. You either have to fabricate your own fingers, or you're gonna have to go to Miller and buy those. So now you're looking at, it's really $300. I think the $350 Miller tool price right here would actually come with the fingers. This tool actually was shipped in a couple other sets to the dealers, so it's not just for this transmission. It's just a universal clutch spring compressor tool, but they added the long fingers so they can get in and reach down and get to some of these parts that are harder to get to. So what I did is, I don't have that tool, so I made my own. On a 6L80, I used a 1, 2, 3, 4 pressure plate. And that's it's a thick plate, and it lays right on top of that D-clutch housing with perfect little ample room to get the snap ring out. And then I use another thing that's found in very commonly in a lot of transmission shops is a sun shell that's been broken, so it's flat on the top for the most part. You know, normally you'd have that ridge right there, that lifted spot. This doesn't have that because that's what breaks off. And then that's about the perfect height for a steel bar to go across there. And by the way, this was bent already, probably from some heavy-handed student. But I take the bell housing bolts and tighten them down evenly, side to side. It'll push this housing down enough to get the snap ring out. And then you release it evenly, side to side. And when you're done, you'll have the snap ring out. And the housing is actually going to lift up and get stuck. The O-ring that goes around the housing is going to get stuck in that same snap ring groove. And that's what the next step here will show you. This is actually in the service manual, but they show you laying a bar, could have been that same bar that I had, laying it across. You put this pry bar in there and you kind of get that hook going underneath the housing. You clamp your vice grip to that bar, give yourself enough room to get a pry bar underneath it, and then pry. and it really doesn't take that much force to come out, but it's not something that you could just get your hands into and pull it out. The O-ring will give you enough of a fit for that not to work, but with a little bit of pry action and that little, I call this a lady's foot, and there's another term for it that's, I guess, politically correct. I don't know if you're allowed to call it that, a lady's foot, for some reason. It's like a oh, I don't remember. It's like a rounded end pry bar or something. I don't know. Lady's foot, that's what it's called. On the C-clutch assembly, one of the only things that's probably worth mentioning is they put this little raised nub right there, and you have to split your snap ring across that. If you didn't do that, for some reason you didn't see it, the snap ring would probably never reach a lot of these lugs, and and then you wouldn't be supporting the snap ring evenly around it. So it's pretty obvious, but I figure it's probably something still worth mentioning. To get this bottom piston out, they actually do have another special tool. It looks like this. This tool here is only like $55, so it's definitely worth buying more than it is making. But if you, for some reason, you were in a pinch or you had a lot of time on your hands, you can get a 3.5R from a 6L80. Almost all these tools can be made from a 6L80. And the steel plate would normally have two teeth between the ones that you see here. So you can kind of imagine what I did. I ground them down and took out 2 teeth. So took out 2, left 1, took out 2, left 1, and so forth. Have to still kind of grind a little bit of this out. And then when you're done, you've got a tool that will go in there and push down on the spring fingers. That's why the special tool is kind of a pain to make, because you don't have enough room. You have to get in here to compress that spring because it's a dished type spring. And there's not enough room to do that unless you have a tool that has these little fingers that stick through there and do that. What I did is, here's the plate before I cut it or ground on it, and you can see I just marked the openings with the paint pen wherever I can go through and push out on that spring. You can see I was able to, if you cut out every 2 and leave 1, it works perfect. So, but you can also see how thick this plate is compared to how it ended up. So I did have to spend a little bit of time grinding between the teeth. A little bit of time at the grinder, but it worked. But it's only, like I said, $57. It's not an expensive tool, so if you have time to wait for it to come in, you're best off just ordering that one. Some of the bell housing side components, we've got the pump and the pump housing, the filter, and the stator support. When you take this apart, you will have a shim that lives between the pump gear down here and the stator support, so don't lose that. This pump is kind of interesting when you go to take it apart. When you first grab it, you're going to see these little snap ring ends sticking straight up at you, and you're like, okay, I just grabbed something and I squeeze these together and the pump will come out. Well, you'll find that these don't want to move. They're really stuck in there. And then you'll get like a screwdriver and you start pounding on these things, and then it finally comes out and it pops out, and then you realize afterward that this plate that's on the end is dished and it works like a spring, and it really kind of preloads and compresses this pump into that housing. So the best way you are probably supposed to take this apart is clamp this, and I use a welding C-clamps. Basically go between the end of that shaft right there and compress this into the housing. Then take your snap ring, your needle nose pliers or whatever, squeeze those in and take it apart. I put a penny here as reference so you can see how small some of these parts are. This is a dual action pump, so they actually suck in and blow out and suck in and discharge. They create suction and then pressure and a suction and pressure on each half of it. That's the way it's shaped like it is. So it's not just like suck it in on one side, blow it on the other side. It has 2 inlets and 2 outlets. Very efficient type of a pump, but it's also, everything's pretty small in this thing. It's easy to misassemble this pump. When you first go back together with it, it'll just go back together and you'll think, oh, that's the way it is. Take a look at the outline here. Notice how that doesn't follow the outline of the centerpiece here? That's assembled wrong. But to look at it, I mean, it does go together, and if you weren't looking closely, even over here you could see where it doesn't quite follow it properly. Now this one's assembled right, and you can see it, the pump body conforms to the little machining that's done in this aluminum end. This is that, you can see that dish that's on this plate fairly well. When you spin this pump, when it's in this condition, it doesn't want to spin. And because this dish plate is pushing out against this E-ring with a lot of force. That's the E-ring that you need to pop off in order to get the pump apart. Which really means you kind of need to compress that a little bit to get that E-ring off safely. Otherwise, it does come off, but you're fighting it because of the pressure that this dish plate is pushing on this whole assembly. That's why I mentioned here, when installing, you'll have to press the pump into the housing. The dish plate on the back of the pump will flex and allow the pump to snap into the housing. And the thing is when this pump is sitting out of the housing and you try to spin the gear, it doesn't like to spin at all. Well, I mean, it does, but you have to like force it. But once you have it in the housing and this dish plate has kind of been compressed down, you've taken the tension off of that E-ring or E-clip, and now it spins nicely, and you can tell it's in there better. If we move to the valve body side of things, there's a clip that we have here. It's like the only clip that they've got under these bolts, so it'd be an easy one to lose. Just be aware that's where it goes. Once you split the valve body, you're going to see there's a lot of these little check valves, and they're kind of neat. You got a red one, you got a few black ones there, black there, a big black one that goes there. You got this blue one right there, this tiny little orange one, a red one, and then you got this weird looking dog bone looking double check ball assembly. You can see these pictures on the side. This will look different, like with the Jeep versus the Honda and so forth. So, hey, everybody's got a digital camera on their phone. It's a good idea to just take pictures of these things when you take them apart, so that way you know you can reference it later. It's a very simple layout that this valve body's got. As I mentioned before, this is where all your solenoids are going into. And those solenoids are going to be working against the valves. Not necessarily all right there, but even the spacer plate's cool, where it looks like they use some fancy laser machine to kind of put these like seals and so forth that we have on there. You know, I don't know if that's a reusable plate, but I have to believe it is, unless when you took it apart it stuck and it tore some of that up. But if it's in a decent shop or a decent shape, it's probably not going to be a problem if you reused it. Another thing that I didn't mention on the previous slide is there are a couple dowel pins that align everything up. It even aligns it up to the case. So they fit in the valve body, and then they actually will center your spacer plate and then the two valve body halves, and they'll stick out a little bit so that it helps center it to the transmission case when you go together. Just for identification purposes, if no other reason, looking at these valve bodies, this is how they're laid out. We have this boost valve and a solenoid limit valve. We don't want to feed our solenoids with max pressure all the time. And then these three right here are pressure regulators for the B, C, and D clutches. So if we were ever running into a problem or we suspected a problem with the D clutch or the C clutch or the B clutch, whatever, we would look at these bores, and we would also look at the valve and the spring, make sure everything is in good shape. We could probably find some passages, the vacuum tests that are in there. Let's see if they're good. On the other half of the valve body, we have these 4 clips that are in there, and you could just take a pick and pick those out of there. But realize they're in there. Like, this valve assembly will not come out until you pull that clip off. And looking at the valves that we have here, this is what they're calling their park lock valve. That's that valve that's hydraulically controlled to move the transmission in and out of park. And also these valves right here are responsible for delivering that pressure. So it's going to take that solenoid pressure from the park lock solenoid and deliver it to the park lock valve, number 1. We also have the C and the D pressure regulator. We got another pressure regulator for those. And the A and F dog pressure regulators. They've got their own little setup. You can see those 2 clips that we're holding their valves in. Flip the valve body around, and we've got the overall pressure regulator going on there, a lubrication valve, and lastly but not leastly, we've got a torque converter clutch valve. On the back side of the valve body, just like on the transmission case, these label out the passages and where they go in relationship to like the clutches and so forth that they operate in the transmission. This might help you if you have to backtrace a circuit into the valve body to make sure you're dealing with the right valves and the right clutches and all that stuff. Some other things worth noting is I did have to make some tools, as I mentioned before, and one of the tools I made right here is a force gauge. If you look at the Miller tool, the Miller tool is like, I think, $150. It's actually not too bad of a cost. There are other ways to do this, and I'm going to probably make some other tools in addition to this one. But when you look at the force gauge that Miller sells, it basically says put 45 pounds of force. It has this, basically looks just like this thing. It has a pressure gauge on it in PSI, and then it has this little cylinder, I guess. And I've just seen line art drawing of it, but I'm like, you know what? I bet you I know what they're doing. They're probably just machined out a bore that is equivalent to 1 square inch and machined out a plug that fits into it. And doing the math, about a 1 inch 130 thousandths bore is equal to 1 square inch. So that's what I did. I went to my lathe and machined out, took a pipe and bored it out to 1 inch 130 thousandths, honed it so it's smooth, then machined out a plug and cut some O-ring grooves in there. And then I took an old AC gauge that we had and filled it with ATF. I didn't like to do it with just air pressure, because if the piston, that has to move really far, but I filled it with ATF and it works great. So 1 pound of force is equal to 1 psi. So now I can put this in between my arbor press or a screw, you know, the threaded deal that we have to release clutches, and we can measure how much force we have by looking at it on the gauge. That's kind of neat. Another one I'm going to make is just using a spring, basically 2 sleeves, and on one sleeve mark like 5 pounds, 10 pounds, 15, all the way up to 50 or something like that. And then you could just compress it and watch it until you're covering the mark, and that would work, I'm sure, just as fine. But one of the things that in order, like this clutch here, this B clutch, is a pain in the butt to measure, and the one I'm doing here on the bottom, actually the B clutch isn't as bad as the E clutch, but this on a 4L60, the 3/4 apply fingers that go from the bottom of the drum and come all the way out and push on the 3/4 clutches on the 4L60, they work perfect. They contact that drum perfectly. And then you just put a spacer up there and your force gauge, put 45 pounds of force, and you can measure the thickness in that gap right there. And it should be, whatever the clearance was. I don't remember, but it's like 50 to 70 thousandths or something like that. But this gives you the ability to do these checks with 45 pounds of force on it. And this measurement actually does change quite a bit. That's like there's only 2 clutches that the force gauge really made a difference on. And it was the E and the B clutch. All the other ones, pretty much, I didn't notice a clearance change, whether I had no pressure or 100 pounds of pressure on it. Measuring right here on the C clutch, you have to use the force gauge as well. So I'm using the threaded rod that you'd use to compress the piston return spring. And you just put something across it that I can put force onto that apply plate or the pressure plate. I used a wrench, a Craftsman, something high quality, and I just keep threading that down until I got 45 pounds of force. And the C clutch, that's that window that you have on the side of the valve body side, so you can actually go in and measure between the snap ring and the plate. I mean, that way you just don't have to stick your hand in here and try to find a spot. You can gain easy access right through that little window, that opening. I measured 35 thousandths on the one I did, and it didn't change at all when I was cranking it up, or when it was at 0 pounds of force just sitting there. I was able to stick a 35 in there, and I put 100 pounds of force on there, and I was able to still feel a slight drag. I mean, it might have changed a couple thousandths, but it wasn't substantial. And when you stop and think about what's going to change it when you put force on it, obviously if you had a bent clutch disc or a bent steel, it would take that out, but really you don't want those in there anyway. So that's not why you're using this force gauge. If you have a wave plate or a dished plate that's supposed to be waved or dished, you're compressing that a little bit. Now I don't know if 45 pounds really flattens it out or if it just kind of gets it partially flattened. But if you don't have a wave plate or a dish plate, it's probably not going to make a difference in your reading. The D clutch housings makes you do some measurements here because you really can't get into the clutch assembly to actually physically measure it. So what they have you do is they have you take your dial indicator right here, or your dial caliper, I should say, and you measure between the case lug and the bottom of the snap ring. And you write down that measurement. And in this case, I got 1 inch 348 thousandths. Then they go over to the arbor press, and you squeeze down on this with the, you stack up your housing and your clutches. And you measure between your bottom steel plate and the ledge or the lip that the snap ring fits into. And you take a look at your measurement there. In this case, I got 1 inch 300 thousandths. So your clutch pack clearance is the difference between the opening that you have between the snap ring and the ledge and the thickness of everything that lives between the snap ring and the ledge, which happened to be 48 thousandths of an inch. And I also did not get this measurement to change no matter how much pressure I put on it. So 48 thousandths is what I ended up getting on this one. So the clearances are important, obviously, to check. Any of these transmissions that are synchronized, where you're releasing a clutch and applying a clutch, you don't have one-way clutches dealing with the stack ups or anything like that, that you got to make sure your clutch pack clearances are within spec. If they're not, you're probably going to have problems, especially on these sophisticated transmissions. But and then some of these special tools are necessary to get the job done. You can either make them or you can buy them, but either way, you're going to have to deal with it somehow, some way. On this transmission, like I said, really it's the B clutch and the E clutch that you really need to do the force gauge measurements on. One more thing that I need to mention here, and hopefully you'll remember it when you go back together. This snap ring is a bear to get out of there because it likes to just move around on you. So when you're doing this measurement, don't do what I did here and have the snap ring in the groove. Leave like 1/3 of the snap ring out of the groove, and then by the time it's over here, it's in the groove, And you could do your measurements over on this side, and that way when you're done, because you have to take the snap ring back out to put everything in it, you can easily just pull on that side and lift the snap ring completely out. I have that labeled in the worksheet, so hopefully if you read the worksheet, it's also shown in the overhaul video. As long as you caught it in one of these 3 settings, hopefully I'll catch it before you guys get the snap ring in there and you have a hard time getting it back out.